All right, in this video we're going to do a problem with an example with a geometric progression annuity that's a little bit more involved than the previous video. I'll step off here and let you have a chance to pause so you can write things down. Okay, so we've got a loan here that's going to be repaid in kind of an interesting fashion. We have 18 annual payments. The first one starts off kind of mundane. We've got $3,000 that's due 1 year from now. However, past that, for the next 7, we're going to increase the payments by 4% over the preceding payment. However, once we get past 8, going from 9 to 18, we're going to decrease the payment by 4% over the previous one. So if the annual effective rate is 6%, what's the initial amount of the loan? So basically here we're looking for a present value, and I think we should probably think about it as 2 different streams. First doing an increasing stream and then a decreasing stream, and then move everything back to time 0. So I've got 2 time value diagrams here, one for increasing payments and one for decreasing payments. So the increasing payments go from time 1 up to time 8, because they tell us the first one is due 1 year from now, and then we have 7 more payments, each of which increases by a factor of 4%. So in our time value diagram at time 1 we pay $3,000. Time 2, we pay 3,000 times 1.04. Time 3, we do 3,000 times 1.04 squared, and so on down the line until we get to time 8, where we have 3,000 times 1.04 to the 7th. We're going to need this last value here because notice that when it says for payments 9 through 18, each payment is 4% less. So I'm going to calculate this off to the side, call it x, just to make the time value diagram be a little bit more easily readable in the second part here. Calculate that x for that final payment. We have a final payment of $3947.7953. Also, when we're doing our present value, we'll need our value for v. We know that I here is 0.06, so our v is going to be 1 over 1.06. All right, so we've got our time value diagram for our increasing payments. Switching over to our decreasing, starting at time 9, the previous payment gets decreased by 4%. Decreasing by 4% is the same as multiplying by 0.96. And then we continue that progression for each time period. So payment 10 is x, that value for x, times the 0.96 squared. So at 17, we've made 9 additional payments. So that's x times 0.96 to the 9th. And then finally, the 18th payment will be x times 0.96 to the 10th. So calculating these 2 present values individually, again, we're going to move everything to time 0. So we've got that first payment of 3,000. We'll multiply it by v to get to because we need to step back 1 year. We've got that 3,000 times 1.04. We'll multiply by v squared, stepping it back 2 years, all the way up to 3,000 times 1.04 to the 7th times v to the 8th. That v to the 8th is moving it back 8 years. Now, using those principles that we've talked about in the previous videos, this is a geometric sum. We want to use our geometric sum formula to be able to help us calculate this. Of course, that geometric sum formula that we have assumes a first term of 1. So we're going to factor out our common factor that we have. We have a 3,000 in every term and a v in every term. We factor out that 3,000v. We get this nice geometric sum that goes from 1.04v, all the way up to 1.04v to the 7th. Those are the terms of the sum. We recognize our common ratio as 1.04v. So we plug it into our 1 minus r to the 8th, the 1.04 to the 8th, over 1 minus r, the 1 minus 1.04v. Calculate all of that. We get a present value of just the increasing payments of $21,201.43. We do a very, very similar thing for the present value of the decreasing payments. We've got the x times 0.96. That was the first payment. That's at time 9, so I've got to step it back 9 years, v to the 9th. Second payment at time 10 gets stepped back 10 years. Likewise, all the way up to the 18th payment gets stepped back 18 years. We have a common factor in all of those terms of x, a 0.96, and a v to the 9th. When we factor that out, again, we see that nice geometric sum, 1 plus 0.96v all the way up to 0.96v to the 9th. Using our formula again for the geometric sum, we get this fraction expression over here, the 1 minus 0.96v to the 10th power over 1 minus 0.96v. Don't forget to multiply by your common factor out front here. and get a value of $14,950. Finally, we're ready to figure out the loan amount. The loan amount is just the sum of the two present values that we just found. Adding those two numbers together gives us a final answer of $36,152.23.